Hello and welcome to another NGen Math 7 lesson by eMath Instruction. My name is Kirk Weiler, and today we're going to be doing Unit 8cc, Lesson 8, on simulating compound events. In probability, there are some types of probability problems that are difficult enough that the math to actually calculate the exact probabilities is either too high of a level for you in middle school, or maybe even too high of a level for basically anybody. Because it's so complicated that you can't really work out the math, and the best you can really do is to do what's called simulation. So we're going to be looking at that a little bit today in a particular case example, all right? This is a very long kind of packet of like worksheets we've got for you because we've got random number tables and stuff like that, okay? But we'll show you how to use them in this particular lesson. So let's get right into it in exercise number 1. A game at the fair has contestants throw 3 darts at a circle that's broken into 10 equal sections as shown. The person wins the game if they get at least 2 out of 3 darts in the shaded area. And let me just kind of emphasize that, right? So at least 2 out of 3 darts in the shaded areas, right? So, you know, I'm sure you've been to a fair before, some kind of carnival, right? They got the carnival games that I never seem to be able to win no matter what, but that's me. Don't worry about me, you know. This particular one, I'm gonna throw darts, right? And I'm gonna win if I throw 3 darts and I stick 2 of them in the shaded area, or all 3 of them in the shaded area. All right, so letter A. What is the probability that a single dart thrown at random will hit the shaded area? Write as a fraction and as a percent. All right, this is pretty easy, so I want you to pause the video and go ahead and answer it. All right, simple enough, right? There are 10 regions, all of the same size. 3 of them are shaded, so if we just look at the number of outcomes in our event, which is, getting a dart in the shaded region, divided by the total number of equally likely outcomes, very, very simple. We're talking about 3/10, right? Now, of course, as a percent, as a decimal, that's 0.3, and as a percent, that's 30%. All right, very, very, very easy here. We're going to work with some nice base numbers here, 30%, right? Now, very important, letter B. If we threw a dart 100 times at the circle randomly, how many times would we expect it to hit? All right, pause the video now and try to answer this question. I hope it's pretty obvious. All right, well, the whole point is, right, if our probability is 3/10, that's the same as 30 out of 100. So that means if we throw it 100 times, we would expect it to hit 30 times, right? So we would expect it to hit 30 times. Okay, but that's just a simple event. That's taking 1 dart and throwing it. But now we want to throw 3 darts, right? And we want to see how likely it is that we will either get 2 of the darts in the shaded area or all 3 of the darts in the shaded area. Now, there is certainly a mathematical way to do this, like a way to calculate the exact probabilities, and I'll give you the exact probabilities towards the end of the lesson. But that math is basically at an Algebra 2 and above level, so kids probably wouldn't see that math until at least 11th or 12th grade in high school, possibly not until college. So what we're going to do is we're going to simulate this. And we can simulate the game from exercise number 1 by using a random number table. Any number from 1 to 30 would be considered a hit. Now understand why that is, right? 1 to 30 is considered a hit because if we've got random numbers from 1 to 100 and we know the probability that we get a dart in is 30%, then 30 out of the 100 should be considered a hit, and 70 out of the 100 should be considered a miss. So we're just going to say that any number in this table, right? So I have a part of the table sitting here. Any number in the table like 7 or 9 or 12, any number from 1 to 30 is considered a hit. Oh, we hit it. And any number from 31 to 100, so 61, 97, 67, 31, 53, all of those should be considered a miss. And again, make sure you understand this. It's a very simple idea. The idea is, well, if I've got 100 total numbers and my chance is 30% that any one dart would hit, then any number from 1 to 30 represents a hit. Any number from 31 to 100 represents a miss. Now, we're going to throw 3 darts. 1, 2, 3. So eventually, we're going to pull off 3 numbers from this table. And it's really imperative that when you look at a set of 3 numbers, you know how many hits you got. So let's take a look at that in exercise number 2. Exercise number 2 is simply just make sure you know how to read a set of 3 numbers from this table. So let's take a look at exercise number 2. If the following strings of 3 numbers are chosen from the table, state how many of the 3 darts hit in each simulation. So remember, anything from 1 to 30 is a hit, and anything from 31 to 100 is a miss. So if I read these 3 numbers off of the table, 58, 24, 56, the only one of these that would be considered a hit would be 1. Now, by the way, I wouldn't win the game here, right? I'm only going to win the game if I get 2 of the darts in or 3 of the darts in. Well, here, if I read these 3 numbers off, 75, 95, 66, none of them are within the 1 to 30 range, so that would represent 0 darts that hit, right? Now here, 19, 29, and 22, all of those are in the 1 to 30 range. All of these would represent hits, so there would be 3, and by the way, that would represent a win. This would represent a loss, this would represent a loss. I know that this problem doesn't actually ask us to make that judgment, but it's good to just kind of realize, because at the end of the day, I'm really trying to figure out what's the probability I'm going to win this game, right? And I'm going to win this game if I get 2 darts in or 3 darts in. So if I get 1 in, that's a loss, 0 in, that's a loss, 3 in, that's a win, right? If I've got 16, 26, and 81, right, the 16 and the 26 are in, that would be 2, and that would also constitute a win. Remember, I just got to get 2 of the 3 darts in. Why don't you pause the video right now and do letter E and F? I know these are pretty easy, but go for it. All right, well, 12, 7, 5, those are all good, right? They're all between 1 and 30, so that would be 3 darts in, that would be a win, all right? 67, 82, and 31. 31's close, but close doesn't count in this case. You've got to be 1 to 30, so none of these would be in, and that would be a loss, right? So if I get 2 in or 3 in, the dart's in, right? I get a win. 0, 1, I get a loss. So it almost seems like it should be 50-50. Do you know what I mean? Right? I mean, if I get 0 in or 1 in, I lose the game. If I get 2 in or 3 in, I win the game. But again, keep in mind, on any given dart, there's only a 30% chance that that dart, randomly thrown, right, lands in the shaded area. Now, by the way, if you have some objections to this because, hey, well, maybe maybe it should have been that, that I'm skilled, so I can aim really well, and it's more likely that it hits the shaded area. Totally, it totally makes sense. We're basing this on the fact that somebody's just walking up and going, throwing 3 darts at random, it hits within that area, what's the probability it hits a shaded area? Now again, what you're going to be doing at this point, right, is you're going to be using that table, right, of those values. And all I want you to do, right, and let's take a look at it in exercise 3, right? We want to simulate the game 20 times. I want you to play the game 20 times, okay? So letter A, randomly pick a place to start in the table. I mean, literally, just put your pencil down somewhere in the table and read off consecutive strings of 3 random numbers 20 times and decide how many hits occur. Fill in the table below. So let's just go back for a moment where we have that picture of the table. And here's again what I mean. I mean, you may want to start sort of in the first column, but you could just start randomly and be like, I'm going to start here, right? And this would be my first set of 3 numbers, 66, 27, 67. And in that set of 3, only the 27 would be a hit. So by the way, I wouldn't win that game, right? but I would have one hit. Then I would maybe move over and I'd go to these three, 82, 31, 31. None of those, right? Now you might say, well, there's only two now left over. So maybe I'd go 53, 12, and 99, right? So I'd do the 53, the 12, and the 99. Well, again, there'd only be the one. The 12 would be the only one that fell in. Still would lose the game. Then maybe I'd come over here and I'd have this set, 4, 13, and 58. Well, in that case, I'd win, right? Because the 4 and the 13 are both hits. All right, that's all I want you to do. But I want you to do it 20 times. I want you to play the game enough so that you start to see which of these categories, 0 hits, 1 hit, 2 hits, or 3 hits, are the most common. Pause the video now and go through this table and simulate playing the game 20 times. All right, fantastic. Well, again, as always, when we do one of these simulations, whether it's flipping a couple coins or throwing 2 dice or whatever, I can't know what results you got, but I can show you the results I got. So when I played the game, and I really did go through it was kind of fun, right? I found that 7 of those 20 times I didn't get anything. 8 of the times I got 1 hit. 4 of the times I got 2 hits, and only 1 of the time did all 3 darts go in my simulation. Now let's take a look at letter B and work it with my results. A person wins the game if 2 or 3 darts hit the board. Based on your results alone, i.e. my results, what is the probability you found of winning the game? Write as both a fraction and as a percentage. All right, so both of these categories result in a win, right? And I had 5 of them. Right? But 5 out of what? Well, it was out of 20. I played the game 20 times, right? And 5 out of those 20 times, I got a win, right? Now, 5 out of 20, right? That's a nice fraction. Okay, I can actually reduce it to 1/4. All right? And that is, of course, 0.25 as a decimal, which is 25%. It's kind of cool, isn't it? We've got what I would call layered percents here. There's a 30% chance that any given dart that I throw will land in the shaded area. But there's only a 25% chance in my simulation, it's my simulation, that I actually won the game, that I got either 2 darts in or 3 darts in. Now, one of the things about simulation, though, is the more we do the simulation, if I didn't do it 20 times, if I did it 100 times, right, or 200 times or 300 times, I would get closer and closer to the true probability of winning this game. So, I'm kind of hoping you're doing this in a class with classmates so that you can get your results along with the results of 4 other classmates. Now, if you're at home right now and you're doing this distance learning, if you've got friends who are also doing it, right, maybe give them a call and find out what their results are. Send them a text, something like that. If you don't have that going on either, it's just you and you alone, then I would rerun it 4 additional times. How do you do that? Grab another random place in the table and read off another string of 3 and another string of 3 and another string of 3. And I know that's doing it quite a few times. I get that. I, in fact, did that in this case, okay? But what I'd like you to do now is pause the video, and if you're working in a large group, find 4 additional classmates, write down their results, and then total them. Then you won't have played the game 20 times, you will have played the game 1, 2, 3, 4, 5 times 20, or 100 times. And 100's, of course, a nice number when it comes to probability. Pause the video now. All right, well, again, I don't know, but these are the results, okay? And again, I did these all myself, okay? And these are my initial table, right? So from the previous screen, I had 7 with 0, 8 with 1, 4 with 2, 1 with 3. When I played it again, I had 10 with 0, 6 with 1, 4 with 2, 0 with 3, etc. And notice, right, I mean, it's not like all the numbers in these columns are the same. This is probably the most consistent column, how many times I got 2 hits, but like we're kind of all over the board here. Now what's important aren't the individual results, but the sum of them all. And again, the big picture here is the more simulations I run, the closer I'll actually get to the theoretical probability, all right? But now I can really see a much better probability. Remember, just me alone, I found 5 out of 20, or 25% of the time I was going to win. Exercise number 5. Based on your compiled results of 100 games, what is the probability of winning the game? Write as a fraction and, parentheses, easily as a percentage. All right, well again, you have different numbers down here, I hope. If you have exactly the same numbers, you either copied them off of my screen or boy, is there a coincidence. Right, but remember, this is hitting it twice, this is hitting it 3 times. Either one of these will work, right? So our probability as a fraction of winning will be 20/100ths, right? And the reason that's an easy percent is that, of course, a percent is just a ratio out of 100. So we find roughly 20% of the time we're going to win this game, right? We're going to either get in 18% of the time, I'm going to get in 2 darts, 2% of the time, very, very small, I'm going to get in all 3 darts, right? For a sum total of 20%. Now, as an aside, I did all of this by just using, the simulation and that random table of numbers from 1 to 100. We could also do the theoretical probabilities, but not using the math that you have. Okay, unfortunately that math is a little bit too advanced, but I thought it would be interesting to actually have the theoretical probabilities up there, and they're a bit messy, all right? But you have an 18.9% chance of getting 2 out of 3 in, and a 2.7% chance of getting all 3 of them in. And if you add those two together, 18.9 and 2.7, what you end up getting is a 21.6% theoretical probability, right? So that's, in theory, I should win this game roughly 22% of the time. And when I played it 100 times, I came pretty close, 20%. If I played the game 1,000 times, I'd be really close to this. Like, I wouldn't be surprised if I got like 210 wins or 217 wins or something like that. I'd expect if I played it 1,000 times to win it 216 times. Think about that a little bit, right? But the more that you run the simulation, the closer the numbers should get to this final probability. And that's one of the big pictures of what we did today. And you're going to do a little bit more simulation in the homework tonight. So let's wrap this up. There are lots of different situations in the real world where the probability is so complicated that you literally have to use random number tables and simulation to try to figure out the probability of a compound event happening. This particular problem, right, one can actually work out the exact probabilities using advanced math that you typically take as a junior in high school. But at the 7th grade level, the best we can do is simulate it. All right, and we can simulate it pretty easily. All right, you'll do more simulation in further probability courses. For now, though, I just want to thank you for joining me for another NGen Math 7 lesson by eMath Instruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.